Hi, and welcome to this topic on transformations. Transformations in our case at GCC are going to be taking shapes such as a square or a triangle, or in this case, as on the screen, a little 2D car, and changing it in some way. Like it's going to maybe move, it maybe going to kind of alter its orientation, maybe both, maybe some other things as well. So what I'd like to do is pause the video and see if you can think about the four transformations I might be talking about here. And then if you've finished, think about any other ones that might be possible. Right, first one is translation. This is when you have your object and you move it maybe to the right and then down. Or maybe you move it to the right and up or left and then up. And what we tend to do is we do tend to say, we don't just say sh like that. We tend to like split it into parts. So we say move to the right and then down. But it's the same sort of thing as if you had moved it straight away diagonally. This is probably the easiest one to apply, but maybe the hardest word to remember out of all of them. So the word translation in this case basically means move, but we always use translation. We don't say move. Second one, well, there's two ones with R, but I'm going with reflection here. Reflection is when you have a mirror line, perhaps like so, and then you reflect it in that mirror line, and this is what happens. It ends up like this. So the top of the car ends up being the bottom of this car. It's a bit like when you look in a mirror, the left-hand side of your face is actually the right-hand side of the person looking back at you. You get this mirror reflection. So for this, we need to know maybe the equation of the line that we are reflecting in, and then we can do our reflection. We'll be looking at that. Okay, third one, rotation. This is when you take your object and you spin it round. Okay, but maybe you spin it round on its axis, but maybe actually you kind of spin it round and it ends up over here as well. For example, on Earth, the Earth is spinning around its own axis, but it's also rotating around the sun. So you can get different, it's more complexity than just spinning it on the spot, basically. And you can also spin it like this way, clockwise, or anti-clockwise. That's rotation. And the last one we're going to look at is enlargement. So this is when you've got your object and you make it larger, funnily enough. Now, you might make it larger sort of in the same kind of position, or it might end up over here or over here, depending on your center of enlargement, and we'll be looking at that. Enlargement also covers when it ends up becoming smaller. And there's also something known as a negative enlargement, which we'll look at in more detail. Others that you might have gone with are a skew transformation. This is not covered at GCC, and it's when like you kind of end up I suppose distorting the car would be one way of saying it. So maybe the top kind of stays at the same height, but then this becomes sort of smaller. But I'm not going to go into any more detail on that. We need to know these four, and I hope you're happy with this little introduction to them. Let's take a look then at translation. So this is when you've got your car and you're moving it somewhere else. And in theory, it's not, this is a 2D car, okay? So it's not changing orientation as well. It's going to stay exactly the same orientation, but just move. But we call it a translation. So my starting activity for you is take this map, start at the shaded square, and use the following translations to find the treasure. Have a go. Right, now here's one I did earlier. So all the different positions after I've done them. So the last one, I got to 10. So a quicker translation to get to the treasure would have simply been to go one up. Very close to the starting point. If you understand that, then you are nearly there with translations actually. There's just like one subtle but important thing we need to look at. But here's a little summary. When a shape is translated, it changes position, but it does not change shape. Another word for that is that it remains congruent. The shapes are congruent, they're exactly the same. So all the vertices, that is the corners of the shape, have moved the same direction and distance. That can actually be used. So you don't have to translate every single corner. You can basically, you could translate your rectangle, maybe just the top left, and it ends up over here. And then you know that because your rectangle looks the same, you can just then draw it in. You don't have to translate all four corners because all the corners move the same direction and distance. Okay, here's the key thing then. We'll look at a concept that captures both the direction and distance that determines the movement of a shape. It's along the lines of what we just did, but actually it's called a vector. So we write vectors like this, and it tells you how much direction to move and by how much. So the thing on top is how much you're moving horizontally, left or right, and the thing on the bottom is how you're moving up and down. So if I was going to look at moving 3 right and 5 up, then instead of writing that, I would write it like this: 3, 5. And you would look at that and you'd be like, that's what that means. It's a more concise way of writing it. Vectors also have lots of other applications. So it's not just like, why are you making up a whole new kind of notation that's confusing? It's I'll talk a bit more about that in a minute. You might want to think, right, if that moves 3 to the right and 5 up, how would I move 3 to the left? How would I move 4 down? So I'll just write that one down. 3 left and 4 down. What do you think the vector for that will be? Well, the answer, 3 moves me to the right, so -3 will move me to the left. Remember, we're essentially on an XY axis, and we know that as we go to the right, X is increasing. So moving to the left kind of makes sense that we're going to decrease our value of X. And then 4 down is very similar. It's going to be -4. So you can see how we can capture right, left, up, down with a very simple notation, positives and negatives meaning different things. Okay, I'm going to test you on this. How about this one? Actually, I want answers to both, but start out with this one on the left. What does this vector tell you? What's going to happen? The answer is a translation. We are moving away from move now. We're going to be saying translation. Right 5, up 8. How about this next one? This one is right 7 and then down 4. Another 2 to try. -3, 2. That is going to be left by 3 and then up by 2. And then 7, 0. This is going to be right 7. And you don't need to say 0 up. You just say right 7 and you're done. If you did write 0 up, that's okay. But as long as you recognize that fact. Okay, flipping it around. How would you write a vector that tells you to complete a translation left 9 and up 4? It's -9, 4. And then this one. Moving to the right, so that's going to be positive. Down, so that's going to be negative. So it's going to be 7, -4. I'm reading it as 7 -4, a bit like you would a coordinate, but it's really important to recognize this is not a coordinate. Coordinates, it's a good time to bring this up. This coordinate tells me a position, 7, -4 on my coordinate grid. So I'd be like here. Whereas this is a vector, this is telling me about a movement. So it doesn't matter where I am on my grid, I could be here, then I'm going to go along 7 and down 4. So notice the difference. We use brackets for both, but we write these vertically. And by the way, we never ever write it as a fraction. I see people doing that. I never do that myself, apart from then. We write it as a column. It's called a column vector. And it denotes a translation in this case. It also has other uses. All right, what about this one? Write down a vector that tells you to complete a translation down 18. Okay, now it's 0 along, so I need to put a 0 there. I can't just leave it blank. It needs to be there. I get away with it before, like I don't need to write it there. but when I write my vector, I need to show that I'm not actually moving up or down. Sorry, left or right, but I am moving down 18. And then finally, this one, translation left by 80, down by 32. That gives me minus 80 and minus 32. So I'm kind of hoping you're buying into this. Actually, it is a really useful way of describing movements just through a couple of numbers, whether they're positive or negative, and then some brackets around them. I don't need to write down all this stuff. I can simply write down the vector. Right, I'm going to start you off this activity, but just do the first one with you. I'll just pick one. So I think I'll go with 4 minus 8. So this activity is asking you to translate each of the shapes by the vectors on them. Okay, it doesn't say that, but that's implied. So translate this shape by 10 minus 3, the vector, and so on. So let's take I'm going to go with this one here. I'm going to shade it just roughly. I won't shade the vector bit out. So 4 minus 8. That means I move 4 to the right and then down by minus 8. So if I just pick the bottom right corner, then I can just count along. I can go 1, 2, 3, 4, and I've moved it 4 to the right. Okay, really important. I'm moving it by like whole squares. I don't count that one as 1. I don't go like 1, 2, 3, 4. No, it's how many it's moving, and it's moved 4 here. And I'm moving down by minus 8. So 1, 2, 3, 4, 5, 6, 7, 8, and it moves here. I could now do all the other ones. And to be honest, it might be a good idea to do one more, just in case you've made a mistake. Because what I'm saying is, what I can now do, actually, I should use a ruler for this to make it look as good as possible. So because I know the right hand corner has moved to there, and I know that it's 1 in width and it's 4 in height, I could actually just draw the shape straight off, and I'm done. However, what I was just saying is maybe just check another one. Maybe I'll check the top left one, okay, the one that's quite far away, just to check that it lines up there, just in case I miscounted, because there is a chance I miscounted once, but probably wouldn't miscount twice, like do it wrong twice. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, and it ends up in the same place. So I'm happy with this one. I can maybe just cross it out now, like I've dealt with that one. Just cross it out as you go, or maybe just put a cross through it. And I've translated that shape. So what I'd like to do is to try it for all the other ones. Just one last thing I'm going to say, and this is quite important. It's not essential today, but it will be in the long run. What we've actually done is followed this vector here. It's actually a little, you can see it as an arrow, a movement. So I've gone along 4, down 8, but this vector kind of exists by itself, and it shows both a movement by with a magnitude and a direction. So that is what vectors are in general. They have a length. That's what I mean by magnitude, and they have a direction. In this case, it's moving diagonally down. And you can do things with them like work out the length of the vector, which would use Pythagoras' theorem, because I've created a right-angled triangle. I could also, in theory, work out the angles of the vector. It's not for today, but that will be coming up. So I just wanted to tell you about that. And if you drew the vector for the other one, it would be exactly the same. The vector exists, and this is actually called a direction vector. There's other kinds of vectors as well, but this is a direction vector. Just kind of throwing these ideas out today. So it's the same vector, it's just kind of, it started in a different place, but they are both the vector 4 minus 8. All right, over to you. Pause the video, see if you can finish it off and translate each of these objects. Pause the video, and then in about 10 seconds, I'm going to show you the answer that you should get. Here goes. So you get the word, move it. If you got that, it's a self-checking exercise. So you probably worked out as it was going on that a word was formed. but you'd see by the end, even without me showing this, that it's going to be correct. So well done. That is the first lesson on transformations. That it's going to get harder, to be fair, but it's important to spend a little bit of time on vectors and the like. We'll come back to those in more detail. The main thing today is that you can now translate shapes using vectors. Well done.